Hi, welcome to Understanding Complex Exponentials, Lecture 4, Relation of Complex Exponentials to Sine and Cosine Functions, Part 2. In this lecture, we'll give answers to the exercises given at the end of the previous lecture, look at multiplying complex exponentials together, and derive a few more useful relations. Okay, let's look at the answers to the exercises from last time. First, e to the I pi. Let's see this two different ways. Okay, the first way. This is of the form e to the I theta, so it must be located on the unit circle at an angle of pi radians. An angle of 2 pi radians is a full revolution of a circle, so an angle of pi radians must be a half revolution, or 180 degrees. This places our point on the x-axis at the point -1. Okay, and the second way. E to the I pi is equal to the cosine of pi plus I, the sine of pi, which equals -1 plus I times 0, which equals -1. This has a real part of -1 and an imaginary part of 0, so it is plotted at -1, 0. So it's good to see that we got the same answer both ways. Okay, next, e to the I pi over 3. The first way? So this time we're rotating by an angle of pi over 3. That's 60 degrees. So our point is located on the unit circle at an angle from the x-axis of 60 degrees. And the second way? So e to the I pi over 3 is equal to the cosine of pi over 3 plus I times the sine of pi over 3. That equals 1/2 plus I, the square root of 3 over 2. This has a real part of 1/2 and an imaginary part of the square root of 3 over 2, so it is plotted at 1/2 square root of 3 over 2. Okay, next, e to the minus I pi over 4. So here we're rotating by a negative angle of pi over 4, so that's 45 degrees. This means we rotate clockwise instead of counterclockwise. So our point is on the unit circle at an angle of -45 degrees from the x-axis. And let's also look at that a second way. So e to the minus I pi over 4 is equal to the cosine of minus pi over 4 plus I times the sine of minus pi over 4. That equals the square root of 2 over 2 plus I times minus the square root of 2 over 2. So our point is plotted at square root of 2 over 2 minus square root of 2 over 2. Okay, our next example is e to the minus 3I pi over 4. Okay, the first way. This example is similar to the previous one, but this time we're rotating by -3 pi over 4, so that's -135 degrees. So again, our point is on the unit circle, and it's at an angle of -135 degrees relative to the x-axis. Okay, and the second way? So e to the minus 3I pi over 4 is equal to the cosine of minus 3 pi over 4 plus I times the sine of minus 3 pi over 4. And that's equal to minus the square root of 2 over 2 plus I times minus square root of 2 over 2. So our point is plotted at minus square root of 2 over 2 minus square root of 2 over 2. Okay, and now for our last example. E to the power of 1 plus I pi over 2. So this example is a little different. It's not of the form e to the I theta, with theta being a real number. So let's write this as follows. E to the power of 1 plus I pi over 2 is equal to e to the power of 1 times e to the power of I pi over 2. Now e to the power of 1 is just e, which is about 2.718. So e to the power of 1 plus I pi over 2 is approximately equal to 2.718 times e to the I pi over 2. Okay, so the first way we're going to look at this, we're rotating by pi over 2, so that's 90 degrees. But now the magnitude, so the distance from the origin, instead of being 1, is e, so approximately 2.718. Alternatively, we can look at it the second way, so e raised to the power of 1 plus I pi over 2 is equal to e times the cosine of pi over 2 plus I e times the sine of pi over 2. And that's just equal to IE because the cosine of pi over 2 is equal to 0 and the sine of pi over 2 is equal to 1. So our point is at 0e, which is approximately 2.718. Okay, now that we're good at plotting complex exponentials, let's learn how to multiply them together. This is actually quite easy. Because e to the a times e to the b is equal to e to the a plus b, we have that e to the I theta 1 times e to the I theta 2 is equal to e to the I theta 1 plus theta 2. So the angles just add. Let's do an example. So here we have 3/2 e to the I pi over 3 times 2 e to the I pi over 2. That equals 3, the 3 comes from the 3/2 times the 2, times e to the I pi over 3, that's the exponential from inside the first set of parentheses, times e to the I pi over 2. That's the exponential from the second set of parentheses. Now we can just multiply those three terms together to get 3 e to the I pi times 5/6, because 1/3 plus 1/2 is equal to 5/6. Okay, let's look at that same example graphically. So we were multiplying together two factors. The first one is 3/2 e to the I pi over 3. That factor is represented by the red dot. The second factor was 2e to the I pi over 2. That is represented by the blue dot. And their product was 3 times e to the I pi times 5/6. That is represented by the green dot. So note that the magnitudes, that's the lengths of the vectors, 3/2 and 2 respectively, multiply to give the magnitude of the end vector of 3. At the same time, the two angles add, so pi over 3 plus pi over 2 is equal to pi times 5/6. Okay, let's look at a few more useful relations. So from the basic relation e to the I theta equals cosine theta plus I sine theta, there are several more expressions we can derive. We've already seen that the real part of e to the I theta is equal to the cosine of theta, and that the imaginary part of e to the I theta is equal to the sine of theta. We can also write cosine theta and sine theta in terms of complex exponentials. So the cosine of theta is equal to e to the I theta plus e to the minus I theta over 2, and the sine of theta is equal to e to the I theta minus e to the minus I theta divided by 2I. You may want to make sure you can derive these from the relation e to the I theta equals cosine theta plus I sine theta. We will use all of these relations in the next lecture. Okay, let's also get the complex conjugate of e to the I theta. For an imaginary number z, which is equal to a plus ib, where a and b are real, the complex conjugate, written as z star or z with a bar over it, is given by z star equals a minus ib. So the complex conjugate of e to the I theta is e to the I theta star, which equals cosine theta plus I sine theta star, which equals cosine theta minus I sine theta, which equals e to the minus I theta. So note that the angle now has the opposite sign. This means we draw the angle by rotating in the opposite direction as before. So on the right, we've plotted 2 points. We've plotted e to the I pi over 3 and its complex conjugate, e to the minus I pi over 3. Both of these points are on the unit circle, but their angles are opposite. Okay, so let's give a brief summary. In this section, we've done the following. We've derived the relation between complex exponentials and the sine and cosine functions. We've covered how to plot complex exponentials in the complex plane. We've covered multiplication of complex exponentials, and we've given a few more useful relations. In the next lecture, we'll demonstrate the utility of these tools by using them to derive angle addition and subtraction formulas.